Hello and welcome back to G Fun Facts Online. Today we are diving deep into a breakthrough that physics has been waiting for over half a century. We are talking about the creation of the impossible fluid. Imagine a cup of coffee that, once stirred, never stops swirling. You could leave it on your counter, come back a week later, and the liquid would still be rotating at the exact same speed, completely defying the laws of friction that govern our daily lives. Imagine a liquid that can creep up the walls of its container, escape through microscopic pores that would block a gas, and conduct heat so efficiently that it effectively becomes thermally invisible. This is not science fiction. This is the reality of superfluidity. For nearly 100 years, this strange quantum phenomenon was the exclusive VIP club of helium atoms. Helium is simple. It is spherical. It is a noble gas that refuses to freeze even at absolute zero. But the universe is rarely that simple. The vast majority of matter is not atomic. It is molecular. It vibrates, it rotates, and it bonds. For decades, physicists have asked a daring question. Can a molecule become a superfluid? Can a complex object with internal moving parts lock into a single quantum state and flow without friction? In February 2025, an international team of scientists finally answered that question with a resounding yes. By creating the world's coldest nanolabs inside droplets of liquid helium, they observed the first definitive evidence of superfluid molecular hydrogen. This discovery has shattered the glass ceiling of low-temperature physics, opening the door to a new era of quantum hydrodynamics, where the rules of chemistry and the strange laws of the quantum world collide. So, let's break down how they did this, why it was considered impossible for 50 years, and why this changes our understanding of matter itself. To understand the magnitude of this 2025 discovery, we first need to look at the contender, molecular hydrogen, or H2. It has always been the holy grail of condensed matter physics. It is the lightest molecule in the universe, and like the helium-4 atom, it is a boson. A boson is a particle that follows Bose-Einstein statistics, which essentially means that at low enough temperatures, the particles stop behaving like individuals and start behaving like a single, collective wave. They lose their identity and merge into a superfluid. However, hydrogen has a fatal flaw. It loves to freeze. While helium remains a liquid down to absolute zero at standard pressure, hydrogen turns into a block of solid ice at a relatively balmy 13.8 Kelvin, which is about minus 259 degrees Celsius. The problem is that the transition to become a superfluid is predicted to happen much lower, around 1 or 2 Kelvin. So long before hydrogen can get cold enough to become a superfluid, it freezes solid. You cannot have a superfluid brick. This is where the ingenuity of the research team from the University of British Columbia, Riken in Japan, and Kanazawa University comes in. They realized they couldn't stop bulk hydrogen from freezing, so they decided to stop it from acting like a bulk solid. They used helium nanodroplets. Think of these as microscopic beads of superfluid helium-4, acting as tiny floating refrigerators. Inside these droplets, they trapped clusters of parahydrogen molecules. Because these clusters were so incredibly small, ranging from just a few molecules to several dozen, they physically could not arrange themselves into a rigid crystal lattice. They were tricked into staying in a fluid-like state at temperatures as low as 0.4 Kelvin, that is far below hydrogen's normal freezing point. But here creates a new problem. How do you prove a microscopic cluster of molecules is a superfluid? You cannot exactly stick a thermometer or a viscosity meter into a nanodroplet that is smaller than a virus. The team needed a smoking gun. They used a molecular probe, specifically a single molecule of methane. Think of the methane molecule as a tiny gyroscope. They embedded this methane inside the hydrogen cluster. Then, by hitting it with precise infrared laser pulses, they could make the methane molecule spin. This is the genius of the experiment. If the hydrogen surrounding the methane was a normal fluid, the molecules would drag against the spinning methane. This is called viscous drag. It creates friction and slows the rotation. In the spectroscopic data, this looks like a blur. It effectively increases the methane's mass, but if the hydrogen had become a superfluid, the viscosity would drop to zero. The fluid would decouple. The methane molecule would spin as if it were in a total vacuum, slipping perfectly past its hydrogen neighbors without any resistance. And that is exactly what they saw. As the researchers increased the number of hydrogen molecules in the cluster, they watched the friction vanish. Once the cluster reached a critical size of about 12 molecules, the methane began to rotate freely. The surrounding hydrogen had decoupled from the probe, effectively becoming a ghost fluid. The hydrogen molecules were no longer individual bumping particles. They had merged into a collective quantum wave function. A superfluid molecule was born. Now, we need to get a little technical to appreciate why this is different from helium. We have to talk about the difference between spheres and dumbbells. Helium atoms are spheres. They are simple points of mass. Spinning a sphere doesn't really change its state. But hydrogen molecules are dumbbells. They have a shape. They can rotate end over end. This adds what physicists call rotational degrees of freedom. In a normal liquid, these tumbling dumbbells collide and transfer angular momentum, creating complex friction. In a molecular superfluid, these rotational energy levels become quantized. The molecules don't just stop moving, they stop tumbling randomly. They enter the ground rotational state. This creates a unique form of superfluidity with texture. The fluid flows without friction, but it still possesses an internal orientation. This opens the door to new phenomena, where the flow of the superfluid and the rotation of its constituent molecules are coupled in exotic ways. Furthermore, to make this work, the hydrogen had to be pure parahydrogen. Hydrogen comes in two spin flavors: orthohydrogen, where the proton spins are parallel, and parahydrogen, where they are antiparallel. Only parahydrogen acts as a true boson at low energy. Orthohydrogen behaves differently and has higher energy. At room temperature, the hydrogen in the air is mostly ortho. To achieve superfluidity, the sample had to be converted to nearly 100% pure para. This purity was a critical requirement for the 2025 experiment. This discovery is actually the closing of a chapter that began during the Cold War. In 1972, the legendary Soviet physicist Vitaly Ginzburg, who would later win a Nobel Prize, alongside his student A.A. Sobyanin, published a paper asking if liquid molecular hydrogen could be superfluid. At the time, the idea was borderline heretical. For 50 years, this prediction remained a physics ghost. Experimentalists tried everything. They tried supercooling bulk liquid. It always froze. They tried trapping hydrogen in porous glass to disrupt crystal formation. That showed hints of weird behavior, but friction never vanished. They even tried compressing hydrogen to metallic states. It wasn't until the development of helium nanodroplet spectroscopy, a technique refined over the last 2 decades, that scientists finally had the tool to test Ginzburg's theory. It took another 20 years to refine the resolution enough to see the subtle spectral slip of that methane probe we talked about. So, what comes next? Now that we have confirmed molecular superfluidity, we can look at the wilder predictions of theoretical physics. One of the most fascinating is the Andreev-Bashkin effect. Theory predicts that if you mix two different superfluids, like superfluid hydrogen and superfluid helium, they will interact in a bizarre way. In a normal mixture, fluids drag each other via collisions, but in a superfluid mixture, there are no collisions. Yet, quantum mechanics predicts they will still drag each other through entrainment. Essentially, if you push the hydrogen superfluid, the helium superfluid will start moving too, instantly, and without any physical contact or viscosity. The two fluids become locked by their interparticle interactions. This is a form of collisionless drag that has only been studied in neutron stars and cold atom gases. Now we might be able to create it in a lab. Beyond hydrogen, the eyes of the physics community are now shifting to the ultimate molecule, water. Water is a nightmare for quantum physicists because it is highly polar and forms strong hydrogen bonds. However, simulations suggest that if water could be confined in strictly one-dimensional channels, like inside a carbon nanotube, and cooled near absolute zero, the water molecules might align their dipoles and form a superfluid phase. The success with hydrogen clusters proves that molecular complexity is not a showstopper for superfluidity, making the dream of superfluid water slightly less impossible. Practically speaking, why does this matter? While we are currently dealing with nanodroplets, understanding the onset of frictionless flow has massive implications. Think about the hydrogen economy. Transporting liquid hydrogen is currently energy-intensive due to viscosity losses in pumps and pipes. If stable metastable states of superfluid hydrogen can be scaled up, we could theoretically pump hydrogen fuel through pipelines with zero pumping energy loss. The fluid would simply coast through the pipe forever once started. Then there are quantum sensors. The technique used to discover this phenomenon, using a molecule as a rotational probe, hints at a new class of sensors. A superfluid molecular gyroscope would be incredibly sensitive to external rotation. Because the superfluid decouples from the container, any change in the rotation of the housing relative to the fluid can be measured with quantum precision. This could lead to navigation systems that are orders of magnitude more accurate than current laser gyroscopes. Finally, there are quantum solvents. Superfluid helium is already used to hold molecules still for spectroscopy. Superfluid hydrogen offers a new solvent with different properties. Because hydrogen interacts differently with dissolved molecules than helium does, it could allow scientists to study chemical reactions at absolute zero in ways previously impossible. We could watch two molecules react quantum mechanically, tunneling through reaction barriers, rather than jumping over them thermally. The 2025 observation of superfluidity in parahydrogen clusters is more than just a new entry in a textbook. It represents the maturation of quantum hydrodynamics. We are no longer limited to the simple spherical approximations of the 20th century. We are entering a world where molecular shape, rotation, and chemical identity play a vital role in the formation of macroscopic quantum states. We have moved from the age of the superfluid atom to the age of the superfluid molecule. And as we peer deeper into these frictionless fluids, we are likely to find that the rabbit hole goes much deeper, into a world where fluids don't just flow, they dance. Thanks for listening to G Fun Facts Online. If you enjoyed this deep dive into the quantum world, make sure to follow us for more detailed explorations of the universe's strangest phenomena.